So this is that deal. So our goal here is to essentially transform all these terms into C numbers, because H has operators in it, but we wanted to convert that to just numbers. So one, of course, is trivial, so we haven't really done much here. But now let's look at H. So the second term has the form of I delta T by H bar. And then we have X of N. The first term is P squared by 2M xn minus 1 plus xn some potential, which we are assuming is a function of just the position operator, xn minus 1. Okay? Sorry. So what do we do next? Because we want to get rid of these operators. If you want to replace P by some number, what should I do? It should act on some state, right?
Take the momentum eigenbasis.
Right. Because this guy acting on this, we don't exactly know what it does. Well, we do, but the way we do it is we then, let's take the first term and do them one by one, okay? And, so ignore the prefactor for now. So xn, p hat squared by 2m, x of n minus 1. And if I now say do delta, sorry, integral of d of p of, say, n and p of n minus 1, then I get x of n pn p squared by 2m pn minus 1 pn minus 1 xn minus 1. So this thing is just going to replace this by either this thing or this value or that value, right? So I'm going to have d of pn minus 1 x of n pn and pn minus 1, and then we'll have pn minus 1 x of n minus 1 times, well, time should not look like x, let's do times the number p squared n divided by 2n. We could have written p squared n minus 1 here. The result would be the same. Why? Because this is a delta function, right? So that's a delta function, so we can use that delta function to do one of these integrals, right? If I do that, then what I'll have, I'll end up with is x, this xn pn, this will be pn, and this will be xn. So just like before, we are going to get these two factors. So we are going to get these guys. Okay, so we're going to get those guys, and I think it's yeah. So we're going to get e squared e to the power I p xn minus xn minus 1, and there's a 1 over h bar. Let me make sure my I is well written. And then there is also p squared n, let's all put n here, 2n. All right? Did we put n here? We didn't. So let's not put n here, because it's an integration variable, right? It's a dummy variable, so we don't have to use the index here. Okay, is this clear? What?
Sorry, what does like p subscripts actually mean? Like, I understand what those
It mean absolutely nothing. You're just like, yeah, we are going to give an interpretation at some point, but they don't really mean much.
Oh, okay.
Well, actually, they will have the interpretation of momentum at that time.
Acha, okay.
Okay. So okay, at some point, we'll actually need those values. So I don't know. Yeah, let's keep them, because I just realized we will need them, because we are going to have the expression for the path integral in phase space coming out first. Okay, so this is our expression for xn, the p squared by 2m x n minus 1. This is small n. So now we go to the second term, which is the potential energy term. And that's easier. Xn v of x hat xn minus 1. So, the argument of v hat can be written as v of x hat plus x hat divided by 2. What we are doing. So, I can apply this guy on this side and this guy on this side, right? And, and v can be a polynomial of, a power series of its argument. And, after the action of the operator, we just get the exact function, right? So as a result, we are going to get xn minus 1 v xn plus x of n plus 1 by 2. This is the average value. Let's call it x bar n. Okay, and then this, we can just do the usual and write this as an integral. So we get d of pn by, say, 2 pi h bar e to the power I pn xn minus xn minus 1 v of x bar n. Okay? So we see that this thing is common to all three terms. So sorry, there should be h bar here. Right? This thing is common to all three terms, right? So if you look at, now what we're going to do is that, for small value of delta t, this thing is the same thing as the exponential. So we take advantage of that fact and we write k xn tn. At this point, you realize that we've been carrying on an infinite number of terms. We are just too lazy to write them. And that's given by 1 over 2 pi h bar integral over, say, pn dpn, and then e to the power minus I by h bar delta t, and then here we are going to get, what are we going to get? We are going to get, first we are going to get, the expression for the Hamiltonian, right? P squared by 2m, and then v of x. So we are going to get an expression for the Hamiltonian for that little, well, I don't know. Let's actually write this out. So we're going to get pn squared by 2m, and then plus v of x bar n, which is the Hamiltonian, right? And then we also have from the first term, from this guy, we also have, now since we are factoring out I, h bar delta t, and that guy didn't have a delta t, so we have to divide by delta t. So we are going to have minus p n xn minus xn minus 1 divided by delta t. Okay. Now, if I look at this, now I take so I have infinite number of these things, right? So in the limit, where n goes to infinity, what happens is that this thing, xn minus 1 divided by delta t, that thing becomes x dot of t, right? And so if I do this, then what I get is k for the whole thing, xn tn x1 t1. We're taking the limit n goes to infinity, and first we have all the position integrals. But then, how many integrals do we have for p? Remember that the p integral is always related to so where does the p integral start? So there will be something here, right? So it'll start at 2. And when will it end? It'll end at n, right? So the p integral is going to be something like d of, not something like, it'll be exactly dpn divided by 2 pi h bar, then d of pn minus 1, 2 pi h bar, dot, 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 integral of dp2, 2 pi h bar, right? So the number of p integral is one more than the x integral, right? So I just realized I made an error in the lecture notes that I posted. Anyway, I'll correct that. And then what we have is exponential, and in the exponential we'll have all these little terms add up, right? So we'll have minus I by h bar. There is a summation for for small n going from 2 to big N, and then there will be, say, pn squared by 2m plus v of x bar of n minus p of n xn, say, dot. Yeah, that's it. And there's a delta t here, which is, what is this thing? This thing is nothing but e to the power minus I by h bar integral from, say, t1 to tn, and here the argument is going to be, this thing is going to be the Hamiltonian minus,
Sir, is this the classical Hamiltonian, right? I
yeah,
mean,
it's a classical Hamiltonian. Because there is no quantum operator inside the path integral. Because by acting on each of these of the kets by the operator, we converted all of them into numbers. So the final expression for the propagator in the phase space is given by d of x of t, d of p of x by 2 pi h bar. So these measures are defined by these limits, okay? This limit. And then we have e to the power minus I by h bar, integral of from t1 to tn of h classical minus px dot d of t. Okay, this is the expression for the Feynman path integral in phase space. Okay, so this is not what we derived last time. The expression that Feynman derived, or well, invented, I should say, was the path integral in configuration space. So we should move on to that. But before that, does anyone have any questions?